Welcome back to the series of lectures on high-performance scientific computing. In the last video, we had started discussing an hardware-agnostic programming approach called OpenACC, where we could parallelize a sequential code using simple directives. Today, we will look a little bit deeper into the syntax of OpenACC. In this module, what we are going to cover is the parallel directive, the kernel's directive, loop directive, the fundamental differences between kernels and parallel directive, and how do we express parallelism in OpenACC. So first we will now look at OpenACC syntax. So the syntax for using OpenACC directives is very similar to the one which we used for OpenMP. In C, C++, you would have a hash pragma, then you would have the ACC directive, and then you would have some certain clauses pertaining to whatever code you would like to do. If I look at the Fortran version of the code, you would have exclamation $ACC, then the directive and some clauses. So a pragma in C, C++ gives the instruction to the compiler on how to compile this code based on the particular architecture. If the compiler does not understand a particular pragma, it can definitely ignore it. Similarly, the directive in Fortran is specially formatted comment that will give the instruction to the compiler about the compilation of the code and what target hardware it should go to. And this can be freely ignored if the compiler does not understand it. The ACC part of it informs the compiler that this will be in sort of an OpenACC directive, or the semantics of it is related to OpenACC. Then the directives are commands in OpenACC for altering the code. The clauses are essentially specifiers or addition to these directives, which help shape the code a little bit. We will see what these are in a bit. So first we will now focus our efforts on the OpenACC parallel directive. So if you look at the explicit programming model, the parallel directive will now instruct the compiler to create what is essentially a group of threads which are organized into a gang, and then it creates parallel gangs on the accelerator. So let's say that you have a parallel hardware which is either a multi-core CPU or a GPU. The CPU, which will now deal with the sequential code, or a single core which will deal with the sequential code until it hits the OpenACC directive using pragma for C++. Then it generates the parallel versions of the bits of sequential code to run on the parallel hardware. Gangs essentially are independent groups of worker threads which work on the accelerator. The code which is now contained within the parallel directive is sort of executed redundantly by all parallel gangs. So if there's a sequential bit of code inside it, then all the parallel gangs will execute that code. So if there will be n copies of the sequential code which will be run inside the parallel gangs. So how do I now express parallelism? So if I have the directive, so when I encounter the parallel directive, the compiler will then generate one or more parallel gangs which will now execute redundantly. So graphically, if I represent it, there will be several gangs like this, 6 of which are shown in this graphic, and they will execute the code. So effectively, it will be something like this. So if you have a for loop which is going from 0 to n, it will ask to do something in that for loop. Each gang will now go and execute parts of this loop. If we do not have any major specifications, each gang will now execute the entire loop redundantly. So now we have to come up with creative ways of separating and portioning out this work. So how do I parallelize a single loop? So first, I will now say a directive called hash pragma ACC parallel, which now within the curly brackets will denote the region where I need to create these parallel gangs. And then I will then identify a loop which needs to be parallelized. So if I use the parallel directive, I usually typically mark a region of code where the parallel execution needs to occur. The loop directive, which is the second directive, is used to instruct the compiler that I need to parallelize the iterations of the next loop which is coming across the parallel gangs. I.e., I need to take this loop, split it up and give it separately to each of the parallel gangs. The parallel region is marked by curly braces in C++ and is marked by a start and end directive in Fortran. So, this pattern is extremely common and you can do all of this with just a single line of code, that you use this loop pattern over and over again. So, you can combine it and you can just say hash pragma ACC parallel loop. Similarly, you can in Fortran you can say exclamation $ACC parallel loop. So, in this example, the parallel loop directive applies to the loop which is following immediately after the directive. In this, the directive marks both the region of the parallel execution and also the distribution of the iterations of the loop. Remember, if you do not do the distribution of the iterations, then the code will run redundantly on these parallel gangs. So, if you apply it to a loop with data dependency, a parallel loop may produce incorrect results, as we have seen in the previous video. So, how do I now start expressing parallelism? So, remember, we create a gang of workers which have a set of independent threads. So, if I now put the directive hash pragma ACC loop, the loop directive informs the compiler which loop to parallelize. And then the loop will be parallelized by the gang of these threads and be run across each gang. So, what if I have many loops? So, I can parallelize it in this way where I can say hash pragma ACC parallel loop for each of the independent loops. So, each loop then should be accompanied by a parallel directive. Each parallel loop can have different loop boundaries and different sort of loop optimizations. And each parallel loop can be parallelized in a different way. This is the recommended way to parallelize multiple loops. If you attempt to parallelize multiple loops within the same parallel region, it may result in performance issues or might give unexpected result. For example, the way I could parallelize this is as mark the whole thing in a parallel region and then say loop for each of those particular parallel loops. That's not the suggested way of doing it. It's recommended to parallelize it in this manner. Now, let us look a little bit deeper into this OpenACC loop directive. How do I express parallelism? So, I mark a single loop for parallelization. I allow the programmer to give additional information about the optimizations of the loop. And I provide many different ways to describe the type of parallelization to apply to the loop. It must be contained within OpenACC compute region, either as a kernels or a parallel region to parallelize these loops. We will talk about what kernel regions are in a bit in this lecture. Inside of a parallel compute region, I have hash pragma ACC parallel within the curly brackets. If I have this particular snippet of code, you see that only one loop is marked for ACC parallelization. So, in this, the first loop is not marked with the loop directive. That means this loop will be run redundantly in parallel by all the gangs. So, this loop essentially will be run multiple times by the parallel hardware. The second loop is marked with the loop directive. That means the loop iterations will properly be split across the parallel hardware and be actually run in parallel. So, you are essentially doing a lot of extra work for the first loop when it is not necessary. If I use the kernels approach where I mark the region using kernels, the loop directive is implied. The programmer can still explicitly define the loops with the loop directive. However, this could affect how the optimization of the compiler happens. The loop directive is not needed but does allow the programmer to optimize the loop themselves. In this directive, the compiler decides on how to parallelize the kernel section. What about nested loops? So, can I parallelize nested loops in this manner? where I put directives for both the inner and outer loops. You should be able to include multiple loop directives to parallelize a multidimensional loop nest. This, on some hardware, will allow you to express more levels of parallelism and increase performance. But in other parallel hardware, this has some difficulty for expressing enough parallelism for doing multidimensional loops. So it sort of becomes hardware dependent. You should be a little bit aware of on what hardware you're running if you want to do this multidimensional loop nesting. The ideal way is to do it that you ignore the inner loops. Sometimes the innermost loop might not be parallelizable at all. For example, if you look at this code, which is a classic code from matrix-matrix multiplication, the innermost loop is not parallelizable. If we attempt to parallelize it without any changes, multiple threads would be able to write to Cij. When multiple threads try to write to the same place in memory, we should expect erroneous results. To fix this, we use the reduction clause. So what happens if you do not use a reduction clause? For example, the innermost loop for k, which goes from 0 to size, you have Cij, which is now getting summed up with Aik with the product of Bkj. For different values of k, you're going to get different product values, but each of it is trying to now going to update into Cij. And if this is done in parallel, what is going to happen is that all of these different k indices are going to update Cij parallelly. When you do this sequentially, the loop runs, each of the loop iteration will take turn to update Cij and you will get the correct sum. But when I do it in parallel, what's going to happen is that all of them are going to try to write to Cij at the same time. The threads we cannot guarantee will take their turns, and you will get an incorrect value of Cij. So to avoid this, we need to use the reduction clause, which is very similar to the reduction clauses which we saw in OpenMP. So we take many values and we reduce it to a single value, such as the summation. It depends on the operator that you want to reduce. So each thread will have their own private copy of the reduction variable, will perform a partial reduction on the loop iterations that they compute, and then after the loop, the reduction clause will perform a single final reduction to produce a single global result. Think about the bag of integers example all over again. So the compiler is very good at detecting when a reduction is needed, so this clause typically may be optional, but may be more applicable to the parallel directive depending on the compiler. So your compiler needs to be smart enough to figure out whether this reduction clause is required or not. So what are the different reduction clause operators that are possible? Very similar to OpenMP and MPI, we can do an addition summation, we can do a multiplication product, we can do max-min, bitwise ANDs, bitwise ORs, logical ANDs and logical ORs. What are the restrictions on the reduction clause? You may not reduce the variable on an array element. So for example, if you look at this bit of code on the left side, you're trying to do the reduction on A0. You're not allowed to do that. You have to do it on another single variable, and then if you would like to assign it to A0, that needs to be done outside the parallel reduction loop. Similarly, the reduction variable may not be a struct member for C or a C++ class member, or it cannot be a Fortran derived type member. Looking at this particular example, you have v.val, which is essentially a struct member, and you cannot do the reduction on v.val. You will have to do it again on some sort of a temporary variable and then assign it to v.val. Now let us look at the OpenACC kernels directive. So in the kernels directive, what it does is that it instructs the compiler to search for parallel loops in the code and then parallelize it. The compiler then will analyze the loops and parallelize those if it finds it safe and profitable to do so. The kernels directive can be applied to regions containing multiple loop nests as well. So for example, if I do a kernel's directive of this sort, this is how I would implement it. In this example, the kernel directive applies for the next loop. The compiler will take the loop and attempt to parallelize it on the parallel hardware. The compiler will also attempt to optimize the loop. The compiler now has a control whether to decide the loop is parallelizable or if it is not parallelizable. If there are many loops, in this example, we can mark an entire region of code with the kernel's directive. The kernel's region is defined by curly braces in C++ and the exclamation $ACC kernels and exclamation $ACC end kernels in Fortran. So you have to mark both the begin and start of the kernel's region. The compiler in this case will now attempt to parallelize all the loops within the kernel's region. Each loop can be parallelized, optimized in a different way by the compiler. The choice is up to the compiler. So if you look at the compiler generated parallelism, what's going to happen is that each bits of the parallel code, different number of gangs and threads will be created, and with the kernel's directive, the loop directive is sort of implied. You do not have to put a separate loop directive for the for loops inside it. Automatically, the compiler will create parallel loops. This process can happen multiple times within the kernel's region. So you can go ahead and do it safely. Each loop also can have a different number of gangs, and those gangs can be organized, optimized completely differently. So for example, the first loop could have a different number of gangs and threads. The second loop could have a different number of gangs and threads. That optimization is left to the compiler. If you look at the Fortran array syntax, this is how the Fortran array syntax looks for the directive. In this, the parallel directive must be paired with the loop directive. The loop directive does not recognize the array syntax as a loop, whereas in the kernel, this can correctly parallelize with the array syntax. So what are the key differences between the kernel's way of doing things and the parallel way of doing things in the directive space for OpenACC? So with kernels, the compiler decides what to parallelize with direction from the user. On the parallel side, the programmer decides what to parallelize and communicates that to the compiler. In the kernel side, the compiler guarantees the correctness of the code. On the parallel side, programmer guarantees the correctness of the code. The kernels can cover multiple loop nests. In parallel, you must decorate or designate each loop nest. If it is fully optimized, there should be no difference between the kernels and the parallel way of doing things. It's just that where does the control lie, whether it is with the compiler or with the programmer. Obviously, as a programmer, if you feel lazy, you should choose the kernel's approach. Compiling parallel code. Let us see now how to go about compiling parallel code. So let's say we have a loop of this sort and we have put in the directive #pragma ACC parallel loop. Now, when I compile it, I will say pgcc -fast -acc. I will say the target is a multi-core CPU, and I'll ask for some information about the acceleration by putting the flag -minfo equal to accel and give the source code. So in this case, the feedback will be that it is generating a multi-core code to parallelize that loop. So this is the parallel directive. It's going to target a multi-core CPU and it's going to generate a multi-core code. It's going to parallelize this for loop, which is going from 0 to n, and it's going to create different gangs where this assignment operation is going to be parallelized. Now, we can do the same thing using the kernel's approach as well. So we say #pragma ACC kernels, where we do not have to mark the loop anymore, and we give the same sort of flags for compiling. It will again detect whether the loop is parallelizable and generate a multi-core code. Now let us see what happens when we give a code which has a data dependency. This is a code which cannot be parallelized because there is a forward dependency. So it's a non-parallel loop. So if I give the kernel's directive, what's going to happen is that when I start compiling it with the same flags, it's going to go and give me a message saying that there is a loop carry dependence and it prevents the parallelization. And this prevents the vectorization of it. So the compiler will no longer create a parallel code, resulting in the correct performance of the code. But if I had chosen to do an ACC parallel loop of the same code, which is allowed from a semantic perspective, but from a logical perspective, what's going to happen is that I'm going to get incorrect results. So if I look at the ACC parallel loop for a non-parallel loop, and I go and compile it, it is actually going to generate the parallel code. So this is the fundamental difference where the correctness of the code, if I do ACC parallel, is the responsibility of the programmer. But if I say ACC kernel, it is the responsibility of the compiler. Here, even though this code has data dependency in the loop, if I say ACC parallel, multi-core code will be created and then you will be able to execute it, getting erroneous results. So essentially, if you use a parallel loop, it's not going to check for the correctness of the parallel program. So the key concepts that you need to understand that there are the parallel directive, there is a kernel directive, and there are the loop directives. You need to understand the key difference in functionality and the use between kernels and parallel directive. When and where to include the loop directives, and how the parallel and kernel directives conceptually generate parallelism. Thank you.